You know the old saying, right? What goes up must come down. And believe it or not, that applies to every single incredible piece of technology we send into orbit. But what happens when one of those satellites runs out of gas and starts its long, slow fall back home? When we see those dramatic headlines about a satellite crashing to Earth, what's really going on behind the scenes? Well, let's get into it. It usually starts with something like this. You're scrolling, and then bam, a headline that sounds like it's straight out of a disaster movie. An uncontrolled object from space, and it's headed our way. It's definitely dramatic, it's a little bit scary, and it makes you ask a whole lot of questions. And we're not talking about something small here. To be exact, the object in that headline weighs 1,323 pounds. To put that in perspective for you, that is literally like a grand piano falling from the sky. Yeah, that'll get you attention for sure. I mean, look at these things. They are complex, brilliant machines doing amazing science hundreds of miles above our heads. But they don't last forever. So what really happens when their mission is over and gravity finally decides to take the wheel? Okay, so this isn't some hypothetical what-if scenario. This is real. There is a specific satellite that really is on its final approach. So let's take a closer look at the object that's making all these headlines. Okay, so this is it. NASA's Van Allen Probe A. For 7 years, it did some absolutely groundbreaking work, studying the radiation belts that shield our planet. But back in 2019, it ran out of fuel. Now its orbit is slowly decaying. But what's really interesting here is that it's coming back about 8 years sooner than anyone expected. And why is that? Well, it's because of a superactive sun, which makes our upper atmosphere puff up, creating more friction, more drag, and that's pulling the spacecraft down way faster. You know, to really get our heads around this whole process, it actually helps to look back at an example from the past. So let's examine a much bigger satellite that made this exact same journey just a few years ago. Okay, say hello to NASA's Upper Atmosphere Research Satellite, or UARs for short. And when I say this thing was big, I mean it was a beast, weighing almost 6 tons. Its re-entry back in 2011 became this huge public event, and it gives us a perfect case study to look at. So every satellite has a story, a life cycle with a beginning, middle, and end. UARS had this fantastic 14-year career doing its science, but notice that last step. Right before it came back down, it was moved into something called a disposal orbit. So what does that mean? So this is the really crucial point. This isn't just random. A disposal orbit is a deliberate, responsible final act. Mission controllers use the very last drops of fuel to nudge the satellite into a lower altitude. And down there, atmospheric drag is much stronger, so it pulls the satellite down way faster. The whole point is to make sure it doesn't become a permanent piece of space junk, zipping around up there for centuries. Okay, so this all seems pretty planned out, which leads to the big question, right? If we know it's coming down, why on Earth can't we just say exactly where it's going to land? Let's break it down. Why is pinpointing the impact zone of a tumbling, multi-ton object moving at over 17,000 miles an hour so incredibly difficult? Well, it really boils down to two chaotic variables. First, the atmosphere itself isn't consistent. The sun's activity makes it literally swell and shrink, constantly changing how much drag is pulling on the satellite. And second, the satellite isn't flying like a neat little airplane, it's tumbling end over end. This means its shape is always changing, which affects how it slices through that unpredictable atmosphere. And the effect of all that uncertainty is just staggering. Even with just 2 hours to go, the potential landing zone isn't a single point. It's a path stretching thousands of kilometers across the globe. For perspective, that's like saying it could land anywhere on a line drawn from New York all the way to Tokyo. And this graph here illustrates the challenge perfectly. See that blue shaded area? 4 days out, the window of uncertainty is huge. Now, that error does shrink dramatically, but it's really only in the final 24 hours that the prediction starts to get anywhere close to precise. So, with all this chaos and this huge uncertainty, we have to ask the most important question of all. How dangerous is this, really? For the incoming Van Allen probe, NASA calculated the risk of harm to any single person on Earth as approximately 1 in 4,200. Now, a number like that, in isolation, it might sound a little bit alarming, but it is missing some very, very important context. So let's go back to the much bigger UARS satellite. After all the headlines and all the uncertainty, its final path ended right here, in the middle of the vast Pacific Ocean, one of the most remote places on the entire planet. And that is the real key to understanding the risk. The odds are just overwhelmingly in our favor because, from a satellite's perspective, our planet is mostly empty. Over 70% of it is covered by water, and huge chunks of the land are completely uninhabited. And here it is, the single most important statistic in this entire explainer. In the more than 60 years of the space age, with thousands of these uncontrolled re-entries, the number of people confirmed to have been injured by falling space debris is exactly 0. A big, fat 0. So, while the risk is incredibly low, the whole issue of space debris is becoming more and more important every single year. Let's take a look at how our approach to all this has evolved. This comparison shows just how much progress we've made. When UARS was launched back in the 90s, there were no official rules about managing reentry risk. Today, the standard is incredibly strict. Any new mission has to be designed to have less than a 1 in 10,000 chance of causing a casualty. That's a huge improvement, and it shows a real commitment to planning for a satellite's entire life cycle. And that really brings us to the bigger picture. We are entering a brand new era with mega constellations launching literally thousands of new satellites. The science has kept us incredibly safe so far, but as the skies get more and more crowded, the central question becomes more urgent. How do we manage all of this traffic to keep space useful and to keep the ground below safe for generations to come?